Welcome everyone to the live interactive session for the post natural gas engineering. Today I am going to discuss some sample problems based on assignment number 6. My name is Ananya Mandal and I am TA for this course. So let's start with the first question, that which of the following statement is false about the centrifugal compression? Option A, higher compression ratio and higher friction loss. Option B, centrifugal compressor's efficiency is high and lubrication oil consumption and maintenance costs are low. Option C, the volume is more than 1 lakh CFM and discharge pressure is up to 100 psig. And option D, centrifugal compressors have relatively unrestricted passages. So we have to find which of the statement is the false about the centrifugal compressor. So the correct answer is option A, that it has high. The false statement is that it has higher compression ratio and high friction loss. And for the other statements, a centrifugal compression is done without any confinement and physical squeezing. So that tells that the centrifugal compression has relatively unrestricted passage. So option D will be the correct will be a correct statement. Whereas the for centrifugal compression, the volume is around 1 lakh CFM and discharge pressure is up to 100 psig. That is also mentioned here. So option C is also a correct statement. As centrifugal compressors efficiency is high, lubrication oil consumption and maintenance costs are low. So that is also a correct statement. Hence, option A is the only incorrect statement, that it has high compression ratio and higher friction loss. So next question is to calculate the water content of a natural gas from the chart by McKetay and Wehe 1958 at a pressure of 2000 psi and temperature of 170 degree Fahrenheit. So this is the chart which gives the water content with respect to the temperature and pressure, where temperature is in degree Fahrenheit and pressure is at psi. So the options are A 180, option B 200, option C 220 and option D 260. So you have to find the water content from this chart made by McKetay and Wehe. So first thing is, the pressure and temperature is known to us, at which we have to find the water content. So the pressure is 2000 psi and the temperature is 170 degree Fahrenheit. So from this chart we have to find out this pressure and temperature. So pressure 2000 psi and temperature 170. So that will be somewhere in the middle of this. So first thing we will do is, at this pressure we find one point at 160 degree Fahrenheit, that is 180. And the other point is at 180 degree Fahrenheit, that is 260. Now the value of water content will lie somewhere between these two, as between these two we will get the value of 170 degree Fahrenheit. So from the chart we get the water contents at 160 degree Fahrenheit and 180 degree Fahrenheit. By doing linear interpolation, we will find out the value of the water content at 170 degree Fahrenheit. So this is the linear interpolation formula. So if we take these 2 points, at 180 at 2000 and 160 degree Fahrenheit, 180 and 2000 psi and 180 degree Fahrenheit, between we will get a relation between these 2 points, and from that we can find out what will be the value at 170 degree Fahrenheit by considering a linear line between these 2 points. Okay, so for that linear interpolation can be used and we will get a value in between these 2 points. So next question is, we have to answer the question number 3 to 5 using the data given below. So the data is that consider a natural gas mixture of 70% hydrocarbon gas, 17% mole percent H2S and 24.3 mole percent CO2 contacting with an aquifer that contains 3% of NaCl. Now gamma G is equal to 0.82 at 2000 psi and 100 degree Fahrenheit. Consider the water content at 14.7 psi and 60 degree Fahrenheit. Assuming 0.6 gravity gas contacting with pure water to be 50 lb per mmcf and assuming gravity correction factor and salinity correction factor as 0.83 and 0.97. Use the provided Witcher and Witcher water content correction for the sour natural gas curve wherever necessary. So the first question, question number 3, according to this data, they are asking to determine the water content of sweet natural gas. Options are A 73.32, B 752.42, option C 33.69 and option D 40.25 lb per mmscf per day. First we have to find the water content of the sweet natural gas. So the water content determination at any given pressure and temperature can be determined by using the gravity correction factor and salinity correction factor. So from that we can get the value of the sweet water content for the sweet gas. So in this question, the water content total water content is equal to 50 lb per mmcf and the correction factors are also given to us, that is the gravity correction factor equal to 0.83 and the salinity correction factor equal to 0.97. So from this equation we can find out the water content for the sweet gas. So W value is known, that is 50 lb per mmcf. CGCS values are also known to us, that are the correction factors. We will put those values and from that we will get the water content of sweet natural gas, that is 40.255 lb. So that is option D. Now with the same data we have to determine the mole percent equivalent of H2S concentration of sour gas. So the equation to find out the mole percentage of H2S equivalent concentration is equal to mole percent of H2S plus 0.7 into mole percent of CO2. So the mole percent of H2S is given, that is 17 mole percent and the mole percent of CO2 known as 24.3 mole percent. So these two values are known to us, from that we can find out the mole percent of H2S equivalent from this equation. So we will put the values 17 plus 0.7 into 24.3. From that we will get the mole percent equivalent to H2S concentration of sour gas, that is 34.01%. So option B is the correct answer. So next question is question number 5, that the saturated water content of sour gas at the given temperature and pressure is. Options are A 64.40 lb per mmsc per day, option B 75.87, option C 81.37, and option D 98.45 lb per mmsc f per day. So here we have to find the saturated water content of sour gas at the given temperature and pressure. So for that we will need this which water content correction graph. For here we will first need the temperature. The temperature is known to us, that is 100 degree Fahrenheit. So we will in this graph consider this line which is for 100 degree Fahrenheit. Next is the curve for percentage H2S equivalent. So in the last question we already calculated the percentage H2S equivalent, that is 34.01. So in this graph, this is 35. So, and next to it will be 34. So this curve is cutting the 100 line at this point. So 34 will be somewhere next to it at this point. So when we will put a straight line from this point, now we need to reach the pressure. So pressure is 2000. So this is the curve for 2000 pressure. So first thing was the temperature. So from temperature we reach to the curve where it is given the percentage H2S equivalent, and from that curve which is cutting the point at the temperature, we will do a straight line and reach the pressure. Now at this pressure, when we will draw a straight line at the left side, we will get somewhere around this point, and that will give you the ratio of H2O in sour gas divided by H2O in sweet gas. Now we know the ratio, and we have to find out the water content of the sour gas. For that, we also need the value of the H2O in sweet gas, which we have already calculated here, which is what is the water content of the sweet gas. So that is 40.25. So here the ratio that we here find is almost equal to 1.6 from this graph, and we have to multiply this ratio with the H2O in sweet gas, which we did in the question number 3, is around 40.25. By multiplying these two, we will find out the H2O in the sour gas, which will come out as 64.40 lb per mmscf per day, which is option A. So in this question, all the values from the previous questions are used, and from that those values, by using this sour natural gas curve, we can find out what is the value of the water in the sour gas. So next question is a match the following, where in the left side are giving certain processes, and for in the right side they are placed different chemicals that are used for that processes. So the processes in the left side are iron sponge sweetening, alkanolamine process, selection process, and sulfenol process. Whereas in the right side, the components they are talking about are option 1, that is mixture of dimethyl etheropropylene glycols, option 2, monoethanolamine, Option 3, hydrated ferric oxide. And option D, sulfuric acid. And fifth, that is mixture of physical solvent, chemical solvent and water. So we have to match these two components with the chemicals that are used for their respective process. So first is the iron sponge sweetening. So it is a batch dry box process with the sponge being a hydrated iron oxide Fe2O3 supported on wood shavings. So we can, from this definition, we can match the first, that is iron sponge sweetening, with the hydrated ferric oxide as the catalyst or the support system which is used for this method. Next is the alkylamine process. So for this sweetening process, different amines are used in gas treating, which includes monoethanolamine, diethanolamine, triethanolamine, methyl diethanolamine, diisopropylamine, and aminoethoxyethanol diglycolamine. So these all types of amines are used for this sweetening process, and most commonly used is the monoethanolamine. So that you can find it in one of the options, that is the option number 2. So these two will be matching to each other. Next is selectional process. It is used worldwide for bulk removal of CO2 and simultaneous H2S removal, and for a low H2S to CO2 ratio. It uses a mixture of dimethyl ether of propylene glycols as a solvent, which is non-toxic and has high boiling point. So the catalyst used here in this process is dimethyl ether or propylene glycols, which is the first option. So we can match these two. Finally, it is the sulfonol process. It is used to remove H2S, CO2, COS, CS2, mercaptans and polysulfides from natural gas process flow sheet, and is similar to amine process. It uses a mixture of solvents, allowing it to behave as both a chemical and physical solvent process. Solvent is composed of sulfolane, physical solvent, diisopropanolamine as the chemical solvent, and water. It's usually used for higher H2S per CO2 ratio, or where CO2 removal is not required to the same extent as H2S. So sulfonol process, it requires both physical and chemical solvents. Hence, we can match it with the option 5. So from all this matching, we can say option D is the correct one. Next question is question number 7. So to identify the incorrect statement regarding the problem caused by water content in long distance transmission of natural gas. So options are A, that the liquid water and natural gas can form hydrates that may plug the pipeline and other equipment. Option B, natural gas containing CO2 and or H2S is corrosive when liquid water is present. Option C, liquid water in natural gas pipeline potentially causes slugging flow conditions resulting in lower flow efficiency of the pipeline. And option D, the water content increases the heating value of natural gas being transported. So we have to find out the incorrect statement of all these statements. So the presence of water in the natural gas causes solid hydrates. It forms a slug flow, causes erosion, corrosion, and also they increase the total volume and decreases the heating value. So these are the different conditions that occur whenever water is present in the natural gas. From that, we have to find out which is the incorrect statement. So the first statement says that liquid water and natural gas can form hydrates that may plug the pipeline and other equipment. So which is the correct statement, as it will form solid hydrate. Next is the natural gas containing CO2 and H2S is corrosive when liquid water is present, which is also correct, as it causes corrosion. Liquid water in natural gas pipeline potentially causes slugging flow conditions resulting in lower flow efficiency of the pipeline. So it does form a slug flow. And finally, that water content increases the heating value of natural gas being transported. This is not correct, as it increases the total volume and decreases the heating value. So option D is the incorrect statement. So next three questions are based on the given data. So answer the questions 8 to 10 from the data in the paragraph below. So compressor with an overall efficiency of 0.75 is used to compress 2 mmCFD of a zero point 0.7 specific gravity natural gas from 100 psi to 70 degree Fahrenheit to 2500 psi. The intercoolers cool the gas to 90 degree Fahrenheit. So additional data, they are giving the critical temperature, critical pressure, isoentropic exponent, that is the K value, and also with different pressure, that is 100 psi, 500 psi, 2500 psi, what will be the compressibility. So from this data, we have to find out the compression at the first stage and the second stage, the brake horsepower required, and the temperature drop between the first stage and the final stage. So we have to find these three values. So the procedure of preliminary calculations for selection of a centrifugal compressor is summarized as follows. So the first step is to calculate the compression ratio based on the inlet and discharge pressure. So if the inlet and the discharge pressure are known to us, we have to find out the compression ratio. Based on the required gas flow rate under standard condition Q, estimate the gas capacity at inlet condition Q1 by ideal gas law. Find a value for the polytropic efficiency EP from the manufacturer's manual based on Q1. Calculate polytropic ratio N minus L by N using this equation, and calculate the discharge temperature by the equation T2 equal to T1 R to the power RT. Next is to estimate the gas compressibility factor values at inlet and discharge condition. Calculate the gas capacity at the inlet condition Q1 by the real gas law. Repeat step 2 through 7 until the values of Q1 converges with an acceptable deviation. Calculate the gas horsepower by the given equation. Some manufacturers present compressor specification using polytropic head in lbf per feet per lbm defined as this, where R is the gas constant given by 1544 by MWA, apparent molecular weight, in psi feet cube per lbm degree Rankine. The polytropic head relates to the gas horsepower by the equation where the mass flow rate in lbm per minute. And finally, we have to calculate the gas horsepower by HPV equal to SPG plus del HPM, where del HPM is mechanical power losses, which is usually taken as 20 horsepower for bearing and 30 horsepower for seals. So this is the steps for calculating what type of centrifugal compressor we have to use. So we have to use these steps also to find out the values that have been asked in this question number 8 to 10. So the data which is given to us in the question is the initial pressure P1 equal to 100 psi, final pressure that is 2500 psi, temperature is 70 degree Fahrenheit. Critical temperature that is 385.63 degree Rankine, critical pressure 668.50 psi, isentropic exponent K given as 1.28, specific gravity of the gas equal to 0.7, gas flow rate is 2 mmcfd, compression efficiency that is 0.75, compressibility factor different pressure is also given, and it's from these all given data we can find out the overall compression ratio, that is R equal to the final pressure divided by the initial pressure. That is 2500 divided by 100, we are getting R equal to 25. Now, because this value is greater than 6, that means that we need more than one stage for the compression to occur. That's why we consider two stages for the compression, and by putting the value and from for two stages we can find out the value of the compression ratio. So when we will use the inlet pressure and final pressure for two compression systems, the R value is coming out as 5, so which is lesser than 6. So we consider that there will be two compression units used for this process. Now the gas is compressed from 100 psi to 500 psi in the first stage, and from 500 psi to 2500 psi in the second stage. As the R value is equal to 5, which is the final by the initial pressure difference. So if the value is 5, then for the first compression, the difference will be 500 divided by 100 will be equal to 5. As 100 we already know, from that we find out that the outlet pressure for the first compression will be 500, and taking that 500 as the inlet pressure of the second compression, the outlet will be 2500. So that the R value for both the compression is equal to 5. So from the given critical temperature and pressure values, we can find out the reduced temperature that is equal to temperature divided by the critical temperature, and the reduced pressure at the 100 and 500 psi, which is pressure divided by the critical pressure. So the theoretical horsepower required is given by the following formula. So in this formula, the values that are required are the K value, which is known to us, that is the isentropic exponent. TB and TB are the standard temperature and pressure. T1 is the initial temperature, which is known to us, that is 70 degree Fahrenheit. T2 and T1 will be varying for both the compressors, both the stages. So according to first stage, we will take P2 as 500, P1 as 100, and for second stage, P2 will be 2500 and P1 will be 500. Z1 is the compressibility factor, which is already given according to different pressure. So for 100 and 500 pressure, we know the compressibility factor. So that will be different for both the stages, and K value will be similar. So we will put all these values from that for both the stages, first stage and the second stage. We will find out the theoretical horsepower required by that stage. So the first stage, the value is coming out as 89.24 HP per mmcfd, and for second stage it is 82.04 HP per mmcfd. So this will answer one of the questions that has been asked before. That is, what is the theoretical horsepower for each stage. Now the total theoretical compression work is equal to the sum of these two horsepower, theoretical horsepower. So that will come out as 171.28 HP per mmcfd. From this value, we can find out what will be the required brake horsepower. So that will be this value divided by the efficiency of the compression. So compression efficiency we know, that is 0.75. So we will divide the theoretical compression horsepower that we get by the efficiency, and from that we will find out what will be the required brake horsepower. So theoretically is an ideal condition, but none of the compressor works at ideal condition. So to find out the real value of the power required, that will be always higher than the theoretical value. So we will have to divide it by the efficiency of each stage. So as there are two stages, so we have to uh, consider that also as the quantity into the total theoretical compression work divided by the efficiency, and from that we will find out the brake horsepower, that is the amount of energy that has to be given for this whole system to work. So that will come out as 456.75 HP. This is the required brake horsepower. Now is the temperature difference. So the discharge temperature after each stage of compression is found out by this equation. So the final temperature can be found from the initial temperature, the final and initial pressure, and the value of Z and K, compressibility factor and the exponent, isentropic exponent. So for the first stage, the T2 value as the initial temperature will be same for both these conditions, only the pressure difference will be different. Here it will be 2500, and this will be 500. But the difference will be same for both of them, that will be 5. So P final by P initial will be equal to 5 only. And the Z1 value, the compressibility factor, we have to consider according to 100 psi and 500 psi. That will be changed different for both the stages, and K value will be same. So from that we can find out what will the final temperature for the first stage and the second stage. So the for first stage it is coming at 318.13 degree Fahrenheit. Our second stage is 299.7 degree Fahrenheit. So from these two values, we can find out the temperature drop between the first stage and the second stage. That will be delta T equal to T3 minus T2. So the difference between these two temperature will be the temperature drop between the two stages, that will come out as 18.43 degree Fahrenheit. So we find out the answer for all the questions. First question was to find the compression at the first stage and the second stage, which we found as the option C, 89.24 and 82.04 HP per mmCFD. Second question was to find the brake horsepower required. So that we found at option A, 456.75 HP. And finally they asked the temperature drop between the first and second stage, first and the final stage, which is option B, 18.43 degree Fahrenheit. So that will answer all the three questions. Like, meeting also. Meeting also. तो बैठ के थोड़ी नहीं मिलेगी। फिर प्रोटेस्ट लास्ट में जाकर फॉलो कौन देता है लेकिन वो लिंक बन गई जी इसको तो 40 मिनट की यूट्यूब में डालना मैं सब ब्लैक डाल कर तो 40 मिनट जा सकता है ना लेकिन हम शायद से सामने पढ़ा देते हैं शायद इसमें से दस देखा जाए और सिर्फ आइडिया सर रिकॉर्ड करने से वो बंद हो गया था मैं 5 6 बजे खोला था मैं खोला था 6 5 बजे आता है 6 5 शुरू हो मैम को फोटो स्टॉप के साथ सेट कर दो तभी तो मैंने मीटिंग में सबका फोटो खींच के लाई थी सामने कैसे लिखना है वैसे इसको काम नहीं किया एक बार बोलूँ मैं मैम को काशी को बोलना आपको बोलो उससे पढ़ काशी को बोल देने मैम को बोल पानी की दुकान लग मेंटेन कर तो आकाश नहीं मैम ने वो व्हाट्सएप में मैम देखा मैम ने वो व्हाट्सएप जो अपन से पेमेंट करनी मैम को बोल ऑनलाइन सब लोग आ सकते हैं बहुत लोग तो ज्ञान नहीं होता मेरा उनको आ जाता है मैम को देखना है कैसे होता है एक था मेरा उस एक प्रोटीन के लिए तो उनको कॉफ आया था 50 प्लेट नहीं उस को बैठ चाय चाय जो रिसीव कर सकते नहीं कॉन्फ्रेंस रूम बड़ा सा टीवी है के नीचे नीचे सीढ़ी से तरफ ऑफिस है ना उधर की उससे कॉन्फ्रेंस एरिया जितने पहले तो जो आया चावल पैरिस में मिलता है इंडिया में और समझते हैं क्लास में क्लास 1 2 में पढ़ा होगा ये समझ नहीं आता कि कैसे कहाँ पीएचडी करना है कैसे लास्ट ईयर में पहुंचे कैसे तो बैठ जाना खाता नहीं करना तो काम कर लेते हो पेटेंट लिखना शुरू कर दो प्रैक्टिकल एक्सपेरिमेंट करना डिजाइनर एक्सपेरिमेंट कबाब कौन सा भी स्टूडियो का ये अच्छा बोलो चलो वही कर लो अच्छे से कितना दिया तो सर वही कर लो अच्छा ऑनलाइन हाँ वो बोल रहे हैं आज सोच रहा हूँ तो यहाँ से खेलने हैं, कल खेलने हैं, कल खेलने हैं, आज मैं काम कर रही हूँ।